Hey guys, what's up? This is Soham Kumar Agrawal. Welcome back. So today we are going to talk about chemistry of the noble gases. Yeah, chemistry of the noble gases. Noble gases we also call it inert gases. So these are like the gases helium. Wait. So yeah, helium, neon, argon, krypton, xenon. We will talk about all these gases, right? We will not talk about the radon because it is radioactive, right? So, one more thing that I want to tell you that I will talk about the main portion of the noble gases, that is the chemical reactions. What I say, I will talk about the chemical reactions part, which are important from the entrance examinations point of view, right? So we will deal uh, them, okay? So before starting, I want to tell you that the natural abundance, the natural abundance, right? That means uh, the percentage, how much percentage that particular gas would be found in the nature, or yeah, in the earth, right? So this is the natural abundance. So just very precisely I will just write the relative order, right? That you know very well, might be you know or do not. Argon is the most abundant gases or in the inert gas family, right? Or say the group 18 family, right? So argon, then neon, then helium, then krypton, and then xenon. This is the natural abundance order of the gases, of these gases, right? Okay. So now the among the family of the noble gases, in the examination, what they usually ask is all about the xenon and its reactions, right? Xenon and its reactions. So primarily we will look upon them, okay? So one more thing, that how this xenon reactions come into play, because initially these gases are said to be inert. Why they were said to be inert? Because they do not react, because generally they do not react, okay? So but 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 what the scientist found, that one of the experiment one scientist was performing, where this inert oxygen was showing the reaction with the platinum hexafluoride compound, and it was forming like O2 plus and PtF6 minus. This was the driving force. This was a turning point when one thought that noble gases elements can show the reaction. What I say, this was the turning point when the scientist thought that the noble gases can show some of the reactions similar to these. All right. So now what happened now, similar kind of reactions the scientist has performed with the xenon, with the platinum hexafluoride, and there was the magic, and the magic was that the xenon plus and PTF6 minus. Similar compound the scientist has got. Scientist has got the similar compound. All right, this xenon reacted with the platinum hexafluoride and give this one as similar as this reaction was thought, or say was being carried out. Okay, now, so this is the basic that you must know, why the noble gases, how the noble gases come into the domain to show such kind of reactions. All right, so this is the basic. I think you must have this much idea about the reactions. Now we will be going to look up over the reactions of xenon. Reactions of xenon. Why I am specifically putting more emphasis over the xenon? Because it was the only element which has shown the reactions which came into so much applicative, or say which come out to be most useful in our industry. All right, in our industry, the xenon reactions found to be very much useful. That's why in the entrance examinations the institutes ask such kind of questions. All right, so I will be putting more emphasis over the xenon. All right, so beginning with the xenon reactions. So again, beginning with the preparation of the xenon compounds. All right, begin with the preparation of xenon compounds. All right, preparation of xenon compounds. The first preparation method is that you have the xenon and then having the fluorine and one catalyst, nickel plus 2 catalyst. Plus 2 means nickel F2. That means nickel is in plus 2 oxidation state, and the ratio you will be having 1:2. If you will be having 1:2 of the xenon and fluorine in the presence of the nickel difluoride, you will get xenon fluoride, GF2 compound. You will be getting GF2. Similar kind of reaction. You will be getting the similar product if you are having xenon and fluorine, but now you are having 1:1 composition of the xenon and fluorine, but now you are applying the electric discharge. Then what you will be getting? You will be getting exactly the same product. That means xenon difluoride. Okay, so you can learn, or say remember it just by that. If you will be having nickel plus 2, then one composition will be, you have to take in the 2 ratio. All right, 2 times of the first one. If you are having plus 2 oxidation state catalyst, right? But at the same time, if you do not have any catalyst, then you have to take single ratio, right? Now the third reaction, that is, this was the second, now this is third. So third reaction is, you will be having same xenon and fluorine, and now you are carrying out the reaction in sunlight. So sunlight, this reaction occurs and exactly same composition, 1:2, you will be getting same compound, GF2. The fourth reaction, xenon plus silver trifluoride. This is important reaction. It has the net and jam has asked many times. Here you have to take anhydrous HF. Anhydrous HF means source of the fluoride ion. Here also you will be getting same compound, that is xenon difluoride. Now moving ahead, one good reaction and I think it has been asked in many places, sorry, in many entrance examinations. Now here you are having xenon and fluorine. Now you are going to just change the ratio. Merely changing the ratio, you will be getting different products. Now see how. Okay. Okay. So if you are having 2:1 and putting the reaction condition in 400 degrees centigrade, 400 degrees centigrade, and in the presence of the light, you will be getting the same compound. All right, you will be getting the same compound, but at the same time, if this reaction persists for a long time, then you will be getting your tetrafluoride compound, GF4. Yes guys, you heard very right, GF4. Now if you increase, or say if you add the fluorine from outside and maintain the temperature up to 300 degrees centigrade, then you get hexafluoro compound, hexafluoroxenon compound. If you add more fluorine to your reaction mixture, then you got again the hexafluoride, and you will get also directly, you can also get directly this product from your initial mixture if you are keeping the 1:20 mixture. If you are keeping 1:20 mixture at 500 degrees centigrade, if you are keeping your reaction mixture in 1:20, then you will be getting your hexafluoride. But at the same time, if you now decreases, now you had decreased your concentration. That means now here you had taken 1:20, and now if you will take 1:5, then you will be getting at 400 degrees centigrade, you will be getting your tetrafluoride. If you have kept 1:5 concentration. That means you have decreased the concentration of the fluorine. That is why you are getting less fluorine in your desired product. That means here you are getting 6 fluorine atom with your product, but now here you are getting 4 fluorine in your product. Am I clear or not? I hope that you people have understood very well. Alright. So this was gazab thing. Gazab. Okay. Now we are going to study the reactions, because this was the preparation part. These are the preparation part. Now we are going to study the reaction part. What? Reaction parts. So put the heading reactions. Okay. Now the first reaction, that is hydrolysis. Most very important. Mark it guys, very important. Mark it guys, just do it now. Mark it now, very important. Alright. So what is the reaction? Reaction is that when you will put xenon hexafluoride with water, I am writing the balanced equation, then you will be getting xenon trioxide, xenon GO3, okay, and 6HF. Okay, 6HF. This is very important, and this GO3 is an explosive. ओह, क्या हो रहा है? Explosive. Okay, explosive. And you will be getting fluorine. So mark one thing. I am just telling you the trick how to learn that here 6 fluorine atoms are there in your reactant. That means in the product you will be getting extra fluorine. That means 6 fluorine, 6HF. Now see what I just told you will be coming in the use. If you are having xenon tetrafluoride and you are treating with the water, then also you are getting GO3. Then you are also getting GO3. Then how you will we know, how you come to know that in your reaction that whether the reactant was xenon tetrafluoride or xenon hexafluoride? How you will come to know? How you will come to know that in your reaction mixture what reactant, whether it was xenon tetrafluoride or it was xenon hexafluoride? That how you will come to know? So I have had what I told you, that here if you have more and more fluorides, that means hexafluoride, then in the product you will be getting 6HF, that means extra fluoride ions. But at the same time, in this xenon tetrafluoride, you have less number of fluoride ions. Then in the product, you will not be getting any fluoride ion, and you will be end up with this product, xenon plus O2 plus H2O. So this is a very good trick. This is a very good trick to learn this. This is a very good trick to learn this. Okay, I hope I am clear now. Okay. Now, another important reaction of this xenon trioxide. So xenon trioxide, when you will treat with base, strong base, mark it guys, mark it, strong base, then you will be ending up with Na4GO6. Na4GO6, you can also write it GO6 4 minus, because 4 and 4 Na plus, 4 Na plus, then 4 Na 4 negative ions. All right. So now important. See, very important reactions. These are very important reactions. What I am telling you, these are very important reactions. You can also get the same if you are having the xenon hexafluoride. You can also do the same reaction of xenon hexafluoride by putting excess amount of base, that is NaOH. That means NaOH, you will be end up with your Na4GO6 and xenon and at the same time, if you are adding the H2SO4, if you are adding H2SO4, that means sulfuric acid, if you are adding to this mixture, if you are adding the sulfuric acid, then you will be getting a very new compound, that is xenon tetraoxide. What this is the structure like this. See, this is the structure. See, this is the structure, xenon tetraoxide. This is the structure. 4 double bond O bonded with the xenon will be shown to you, are shown to you. Am I clear or not? I hope I am now clear to you. Okay. So now one more important aspect, that is the preparation strategy or the preparation reaction of xenon OF4. This is also a very important reaction which usually been asked in various entrance examinations, right? So in this reaction what happens? Xenon hexafluoride undergo hydrolysis in the presence of silica. That is, it is the controlled hydrolysis, because we had also seen one hydrolysis where our product, we will end up with the xenon trioxide. Our final product was xenon trioxide, that was the complete hydrolysis. But here what I am saying, controlled hydrolysis. If we will carry out controlled hydrolysis, then we will end up with a new compound, that is GOF4. GOF4, what is its structure? See here. Xenon double bond O, 1, 2, 3, 4. F. Am I clear or not? Okay. Now moving ahead. Xenon hexafluoride, when react with cesium nitrate, very important reaction. Many times it has been asked in the exams. Okay, so xenon hexafluoride cesium nitrate. Cesium nitrate. A limited amount of cesium nitrate has been added. Try to understand. Limited amount of cesium nitrate has been added. You will be end up with xenon OF4. Similar compound GOF4. You will be end up with GOF4. Again, if you are adding more cesium nitrate, then you will be also going to obtain GO2F2. Very, very good compound. And I am telling you the trick how to learn it. I am telling you the trick that how to learn it. You know the structure of GOF4. You know the structure of GOF4. You know the structure of GOF4. See. Now what you have to do? You have to put one more oxygen. You have to add one more oxygen. Then you know oxygen forms double bond. Oxygen forms double bond with a metal. Then you have to eliminate two fluorine atoms. Then you have to eliminate the two fluorine atoms. Then only you will be getting two double bonds with the oxygen and remaining two fluorine atoms. And the two fluorine atoms will be remained. So that is why here I am writing GO2F2. So this is your final product. And one more thing. You also get the same product if you are having different reagent with the different reagent, and the reagent is N2O5. So this, if you are having this reagent with your GOF4, then you will be also getting the same GO2F2. And what would be the structure? The structure would be the seesaw structure. This is the seesaw structure. How this seesaw structure? How you get this seesaw structure? Let me tell you. This is seesaw structure. What I say? This is seesaw. You know what is a seesaw? Let me tell you. The fluorine, since electronegative element, will go in the axial direction. You have read all this. I am here assuming. Okay, the fluorine atom go to the axial, and now rest less negative electronegative element go into the equatorial positions. Less electronegative elements now go at the equatorial positions. So here we are having one lone pair with the xenon. That is why this only structure will be considered, this only shape will be considered, and it is nothing but a seesaw structure. Now one question might arise in your mind that how you got this lone pair. How I have written this lone pair? So very basic trick. We have 8 electrons in the valence orbital of xenon. We have 8 electrons in the valence orbitals of the xenon. So now let me tell you that oxygen forms double bond. This is double bond. 2 oxygen, that means 4 electrons has gone. Now 2 bond, single bond with the fluorine atoms. Now what left? That thing that left is the single lone pair. So that is why this is the lone pair that I am writing it in the, I am putting in the axial position, right? So I hope now this thing is clear to you. Okay. Now some reactions of the GF2. It is also very important. Reactions of GF2. Reactions of GF2. Okay, very important reactions. First reaction is hydrolysis. Okay, now we are going to carrying out the hydrolysis. So here we have GF2. So 3 reactions I will be going to talk to you about. So let me talk it. Okay, first one is the hydrolysis. Let me cover it here. On hydrolysis of the GF2, we end up with the xenon, with the O2, and with the HF. Very obvious. If you are getting only xenon, then the fluoride ions will combine with hydrogen and give you HF. Alright. Okay, so this is very obvious reaction. This was very obvious reaction. Now another reaction, that is ZF2 with iodine. Very important reaction for synthesis of IF5. Very important reaction for synthesis of IF5. So what is its structure? Its structure, C. Iodine have 7 electrons in its valence shell. So each electron gets bonded with the fluorine. 1, 2, 3, 4 and 5. Now what left? Now what left? One lone pair left and 5 bond pair. Okay, so only total 6 electron pair. That means structure would be octahedral. Structure octahedral. Structure octahedral. OH means octahedral, right? And shape would be square pyramidal. Shape square pyramidal. All right, shape will be square pyramidal. All right, so this was the reaction. Now now we have another reaction of GF2 with uranium trioxide. Very important reaction to synthesize the nuclear fuel. And you will be end up with UO2F2, and then finally it gives UF6. This is your nuclear fuel. This reaction is quite important because it associates itself a reagent, that is nuclear fuel. That means in nuclear reactors, and we need this fuel, and we synthesize it by carrying out the reaction with the xenon difluoride with UO3, uranium trioxide. All right, some of the reactions also left. Let me write it so that you have to just mug it up. That the reactions of krypton. Okay, so if you are having krypton, then if you treat with fluorine, then it give you krypton difluoride, and this reaction occurs in light, or say UV region, and 77 degree Kelvin temperature. Okay, so what is its properties? It is a good oxidizing agent and fluorinating agent. This is a good fluorinating agent because it is a good oxidizing agent. That means it wants to get reduced. That means it needs electrons. So KrF2 will convert into the Kr, that is the krypton, and released fluoride ions will act as a fluorinating agent. All right. Okay. Now the second reaction is the KrF2. Now we have synthesized, and when this reaction occurs with the silver, then one important reaction, that is AgF3 we will get, and Kr reduced form. So what I said, that this is the oxidizing agent. It has oxidized the silver into the +3 form. 0 to +3. See, 0 to +3 oxidized the silver from 0 to +3. That is why we are saying that KrF2 is a good oxidizing agent. That is a good oxidizing agent as well as fluorinating agent. Why? Because silver has got fluorinated. That silver got fluorinated. AgF3. Okay, that is why we had said that KrF2 is a good oxidizing agent and good fluorinating agent. All right. Now we have one important reaction, that is the reaction of KrF2 with xenon. So we will end up with GF6. So you can add it in the preparation method of the GF6. Xenon hexafluoride. One important thing I forgot to tell you, that this AgF3 we had used in the synthesis of GF6. See, we had used in the synthesis of see, Here we had used AzF3. Here we had used AzF3 in the synthesis of GF2. Sorry, in the synthesis of GF2 we had used AzF3. All right. So here you can connect all these things for your memory, right? For your memory. Okay. So Xenon hexafluoride we had prepared from KrF2 as well. Now one more reaction, that KrF2 when reacts with iodine, we get IF7. This is very good reaction because at previous what I had told you, I told you one reaction. I told you one reaction where we were getting the IF5. When here we had treated the xenon difluoride with iodine, we were getting IF5. We were getting IF5. Now what we are doing? We are treating the KrF2. We had replaced the xenon with the krypton. We had replaced the xenon with the krypton. Now what we getting? We are getting the IF7. We are getting IF7. In the case of the xenon, we were getting IF5. So here you can see more fluorine. In the case of the krypton, we are having more fluorine in our product. That also proving that KrF2 is a good fluorinating agent than GF2. Xenon difluoride, KrF2 is a good fluorinating agent because it is giving IF7 instead of IF5. Okay. So I hope that this thing is now clear to you. Okay. So one more thing, that the bond energy comparison, that whether xenon fluorine bond or krypton fluoride bond, which one is strong? So let me tell you the data, that xenon fluoride bond is 131 kilojoule per mole. This is the bond energy. Bond energy means the amount of energy you give to the molecule so that that particular bond will get broken. To break a bond, the amount of energy required is called bond energy. In the simple words, to break a bond, amount of energy given or released is called bond energy. So for xenon fluoride, it is the 131 kilojoule per mole you have to give to break this bond. While in the case of the krypton, it is 49 kilojoule per mole. So here you can see that how much strong the xenon fluoride bond is. Here you can see that how much strong the xenon fluoride bond is. So this is the end of the chemistry of the noble gases. Okay, so I will come up with later with another videos having different chemistry of the elements. Okay, so if you like the video, please subscribe my channel and like the video and hit the bell icon so that the incoming video will not be missed. Okay, so see you